Today we discuss this interesting and challenging question. We are given that A is a real number and we have system of two equations. One is x squared plus y squared equals to a squared plus 2, and the other one is 1 over x plus 1 over y equals a. Geometrically, the first equation represents a circle and the second equation represents a hyperbola. We are asked to solve the system when a equals to 0, which I think is a very simple question. And for the second question, we are asked to find the range of a such that the system has exactly two distinct real solutions. This is where the challenge comes from. If a equals to 0, then 1 over x plus 1 over y equals to 0 means that x equals to negative y. And from the first one, x squared plus y squared equals to 2. So 2x squared, because x equals to negative y, will be equals to 2. And x equals to plus minus 1. If x equals to 1, y will be equals to negative 1. If x equals to negative 1, y will equals to 1. So we have two solutions when a equals to 0. For second part, find the range of a such that the system has exactly two distinct real solutions. The range of a must include a equals to 0, because when a equals 0, you have exactly two distinct real solutions. First of all, let us understand what is the meaning of x squared plus y squared equals to a squared plus 2. Geometrically, it is a circle. A circle centered at origin with the radius square root of a squared plus 2. How about 1 over x plus 1 over y equals to a? This is a hyperbola, but it is not that obvious. Let me show you here that this is a hyperbola. 1 over x, 1 over y equals to a. We will multiply everything by x, y over a. So this will be equals to y over a and x over a, and this equals to xy. So xy minus 1 over a x plus y plus 1 over a squared equals to 1 over a squared. For this part, x minus 1 over a, y minus 1 over a equals to 1 over a squared. With this, we see that it is of the form xy equals to some value k. So this is a hyperbola. Y equals to 1 over a and x equals to 1 over a will be the asymptote. So this will be the graph of. Note that x equals to 0 and y equals to 0 will satisfy this equation. But from the original equation, xy cannot be equal to 0. It will mean that this is not exactly the full hyperbola because it does not pass through the point 0, 0. So with this in mind, then we'll see that if a is positive, no matter how small is a, it will always pass through 2 points here. When a is positive and increasing, a squared plus 2 will keep increasing, and it will mean that the radius of the circle keep increasing and the circle become bigger and bigger. Whereas when a is positive and increasing, 1 over x plus 1 over y will become closer to the asymptote. With this in mind, we know that when a is positive and increasing, they will have two intersections here and possible another two intersections there. When a is negative and decreasing, the similar thing happens. So this means that before we go and do the calculation, we know that the range of a must be in between some negative c and some positive d. which pass through 0. I'm going to give you two different approaches to solve the problem. The first one is using the sum and the product of the root followed by the discriminant of a quadratic equation. The second approach is by using calculus. Let me erase this to save some space. Now we let the sum of xy as x and the product of xy as p. For the first equation, x squared plus y squared is actually equal to x plus y squared minus 2xy. And we know that this is equal to a squared plus 2, and this is equal to s squared minus 2p. For the second equation, this is actually means that x plus y over xy equals to a. And therefore, s over p equals to a and x equals to ap. With this, we form another system of equation. Now, we substitute s as ap into the equation here. A squared is a squared, but x will be equal to ap. So s squared is equal to this minus 2p. A squared p squared minus 2p. We form a quadratic equation either in A or in P. Let us focus on the quadratic equation in P. So this will be p squared p and something equals to 0. The coefficient of p squared is a squared, and the coefficient of p is negative 2, and the constant is negative a squared plus 2. Note that when p equals to negative 1, this is a squared. P equals to negative 1, this is positive 2. So when p equals to negative 1, this is a squared plus 2 minus a squared plus 2, and it will be equal to 0. It means that p plus 1 will be one of the factor. Since p plus 1 is one of the factor, it will mean that another factor will be equal to a squared p minus a squared plus 2. And therefore, p equals to negative 1 or p equals to a squared plus 2 over a squared. If p equals to negative 1, then s will be equal to a negative a. If p equals to a squared plus 2 over a squared, then s will be equal to a squared plus 2 over a. Let me copy down the conclusion here. Case 1, the sp equals to negative a, negative 1. Since the sum is equal to negative a, product is equal to negative 1, then we know that x and y are roots of the equation z squared minus the sum, that is plus a, z, and plus the product, that is negative 1 equals to 0. Consider the discriminant. The discriminant is b squared minus 4ac. b squared is a squared minus 4a and c. And this is a squared plus 4. That is always positive. It means that there exists two distinct real solutions, x1, y1, and x2, y2. Let us recall what we want to find for part 2. We want to find the range of A such that the system has exactly two distinct real solutions. For this case 1, we already know that it will exist two distinct real solutions. Then what we want to do is, we do not want to have any real solution from the second case. And it is quite similar to what we have just now, that the graph, from the graph that we have, this is something like this. Okay, no matter how, they will have two answers here with the product of the the solution xy equals to -1. With this in mind, we know that we do not want anything from the case 2. And also note that there may be some arguments say that you have two solutions here, and we may have another one real solution that is exactly the same as the previous solution. This is not possible because the product of the xy here is -1, and the product of the xy here is equals to a positive value. Therefore, they are not the same point. We will change a little bit for case 2. And we wish to say that the discriminant is always negative. Since there should not have any real solution to this equation, that's why the discriminant has to be negative. And the discriminant is equal to b squared, that is a squared plus 2 over a squared minus 4a and c has to be less than 0. Of course, in this case, we do not want a to be 0. Otherwise, it does not make sense here. See that there is a common term that is a squared plus 2. A squared plus 2. That is positive, we can cancel off. There's another common term, a squared and a squared, that we can cancel off. Then we left with a squared plus 2. And here all gone, minus 4, less than 0. So a squared is less than 2. And therefore, a is in between negative square root 2 and square root 2. And in this case, for our calculation here, a shouldn't equals to 0. But overall, when we solve this equation, we should include a equals to 0 from the first part. The final answer will be a must in between a negative square root 2 and square root 2. And this end of the first method, that using the idea of the sum and the product of the root followed by the discriminant of quadratic equation. Now we are going to do some calculus for method 2. Let us sketch the graph for these two curves. As we mentioned just now, no matter what is the value of a, there should be always two intersections here. So we do not want to have any intersection. We want to know when can these two curves tangent to each other. So when we say about tangent to each other, we want to find the grade of tangent, that is dy dx. So from the first equation, differentiate respect to x, it will be 2x plus 2y dy dx equals to 0. It means that dy dx equals to negative x over y. From the second equation, differentiate respect to x, that is negative 1 over x squared minus 1 over y squared dy dx equals to 0. It means that dy dx will be equals to a negative y squared over x squared. Combine these two, we will have a negative x over y equals to negative y squared over x squared, that is x cubed equals to y cubed, and therefore x equals to y. And we probably can see from here that if that is a tangent, then it will happen on the line x equals y. So in particular, when x equals y, what will happen? When x equals y, 2x squared will equal to a squared plus 2, and 2 over x will equal to a. S is equal to 2 over a, so 2 over a squared is equal to a squared plus 2. Multiply each of the term by a squared, this will be equal to 8, this will be a to the power of 4, and this is equal to 2a squared. This is a quadratic equation in a squared, so it will be, let me continue here, it will be a4 plus 2a squared minus 8 equals to 0. A squared plus 4, a squared minus 2 equals to 0, and therefore a equals to plus minus square root of 2. When a equals to square root 2 or negative square root 2, it will be tangent to each other. Okay? So to avoid this, we just need to have a less than this value, because when a is smaller, the hyperbola will be further from the asymptote. With this, then we know that the a should be in between negative square root 2 and square root 2. This is the end of today's lesson. Hope you enjoyed it. I'll see you again next time. Bye bye. Bye bye.